Sure. And so the next question is, how do we evaluate the output speech? So typically we evaluate from the aspects of intelligibility, naturalness, and expressiveness. So we will, more specifically, we will evaluate the prosody, which is related to rhythm or intonation, and also we evaluate the voice quality. And the typical method we evaluate is use both subjective evaluation and objective evaluation. Okay, so we move to the next part, and this is what we are doing today. That is the statistical parametric speech synthesis. And I will covering the front end, back end, and deep learning resolution. Various rules to generate speech. Corpus to generate speech driven from data. So this is the story from 90s. And then the second generation is concatenated speech synthesis, which directly select segments from the recorded corpus and then concatenate these segments together, which is actually still perform very well as far as we know that some of the companies still use this kind of techniques in their production. But because if the segment is absent from the corpus, then the synthesis performance will be affected very serious. So later, researchers turn to use the statistical model to try to offer some more flexible method to generate the speech. This is what we will focus on more today. So here, two representative method is, one is the HMM model and one is the deep learning based model. So typically, a statistical text-to-speech synthesis system is composed of two parts. The first part is the text analysis, which is also called front end, and another part is the back end, that is the statistical parametric synthesis, which try to synthesize the parametric acoustic features into speech waveform. So let's look at the front end first. In this part, remember we try to convert the raw text sequence into a representation that is ready for our next step of synthesizing the speech. So to obtain the linguistic context, which is the descriptor of the speech, like if we have a text sentence, then we need to know how is it like when we like how is the output speech like. So at this step, we need to generate a vector that can specify how is the speech like, right? So like we need to know how is the phoneme, that is how is the pronunciation. We need to know how is the prosody like, how is this kind of things like. But actually it's quite challenging because it's still an open question that what's the effective linguistic context vector. But actually we have some, there are some features that are commonly accepted that are highly related to the output speech, like what we were talking later, the PostTaking, the prosodic international shapes. So without further waiting, let's go through some of the typical techniques we will use to generate the linguistic context vector from the text. Okay, now the input is the raw text. As we know, in the raw text there is different kind of symbols. We need to remove these symbols and replace with some correct pronunciation, like digit, like symbols. And Actually, here the key challenge is the disambiguation by using the context. Because, for example, here, like 3/8, it can be a number, it can also be a date. So whether it's number or whether it's date, it should be depending on the context it is used. So the mainstream method is based on rules, that because rules can solve most of the cases, but we should say lots of some of the cases that should rely on longer context. So statistical methods try to play such a role. And next step is, if we have the sequence of text, if we know how to segment this long text sequence, then it should affect the output speed very much, because actually at the boundary of the words, when we utter the speech, we would give smaller or larger pause at the boundaries. So here the boundary information is also important. And especially for Chinese and also Japanese and Korean, there is no obvious word boundaries. So we need to use some method to extract this boundary. And the mainstream method is like lexicon based. We can search in the dictionary for the words, and then we can obtain the boundary. But some of the case still there is some disambiguation. So we also need to rely on the longer context. And this is the topic, the common topic go through from the different components of the front end, because we need more context to solve the disambiguation. So the next step is the post-taking. As we mentioned, that because the different function of words should lead to different pronunciation. Like if we look at the word record, if it's a verb, then we pronounce record the video, and if it's not, then we pronounce video record. So so here, based on the segmented words, we assign the post-taking labels. But recent research try to combine the word segmentation and post-taking together, because these two parts is highly related, and when they are jointly optimized, the performance will be improved. And the next step, when we have the words and they are post-taking, we are concerned with the pronunciation. So like the phonemes, or in Chinese, the syllables are used. So from the sequence here, we would like to convert it into the syllable sequence. And here the challenge is the polyphone disambiguation, coarticulation, and alpha merging. And here is the typical flow that the conversion is conducted. So like if we have a dictionary, then we try to search the word. If it is in the dictionary and the pronunciation is unique, then the problem is solved. And if we need more context to determine the pronunciation, then we go through the statistical model. And here the decision tree is one of the powerful methods in this task. And the next topic, prosody, is actually it's a difficult topic, because we may need another tutorial to talk about prosody. But actually, in text-to-speech, we are concerned with what information we need to provide for the acoustic model. We may not need to specify like intonation very specifically, we just need to provide what information you may use for synthesize the final intonation. So here, lots of the work are focused on the prediction of focus, prediction of pitch essence, stress, and also some words are related to predict the breaks, like what we say, when the breaks are placed at the boundaries. And also one of the famous structure for prosody prediction is to predict the hierarchical prosodic structure. The structure is a hierarchical structure that contains the layer of syllable, words, phrase, and utterances. And it's interesting that according to some research, it is shown that when human utter speech, the intonation has a declination effect. And also at the beginning of every phrase, there is a restart. You can observe there is a raise at the beginning of every phrase. So this is, we hope that we can synthesize such kind of effect in the upper speech. So the hierarchical structure is like this, and so it's like a tree that has multiple layers, as we said, syllable, words, phrase, and also the intonational utterance. So we do a little experiment that if we use the prosodic structure information in the text-to-speech system, will it affect the results? And we see that this figure is showing the pitch of the speech that is generated with the model using prosodic structure. And you can see that we can observe the restart in the pitch counter. Okay, so here is what we got now. We got the linguistic vector, including the phoneme, the syllable, the structure of the prosody, and we represent it as like the numbers, like the syllable forward position in the word or in the phrase. Now we will base on this linguistic vector and then see how to generate the speech. That is the story of backend. So in the backend, we want to convert the linguistic vector into the speech. But what we will convert, it's actually the acoustic features. Let's denote first the linguistic feature as X and the acoustic feature as Y. Then the program is formulated as Py given X. And it is approximate as this. What does this equation mean? It means that when we are generating speech, we only focus on the sequence that is the most probable sequence. We will elaborate it in more detail later. So first, let's look at what is the output acoustic feature we will generate. So typically, the vocoder that is to generate the acoustic feature from acoustic feature to speech and also extract acoustic feature from speech is based on the source filtering model that is trying to mimic the human speech production process. As lots of you already know, so I will not spend much time here. But so here I would like to try to show you some. I would like to try to. So here is So the pitch is composed of the part of periodical pulse and noise, and these two parts of source will go through the filters, that is modeling our vocal chat and to the upper speech. Let's look at what is the sound like. Can you see my point?
Author of The Danger Trail,
This is
Philip
the-
Steele's, etc.
Yeah, this is the speech. So that means if we have this kind of parametric features, then if we generate this kind of parametric features, then we can use the vocoder to generate such kind of speech. So how do we obtain the features, the filtering features? One of the simple method is the linear predictive code. So in this part, it's trying to predict current signal tone based on several previous samples in such an equation. Let me find a point. In such a kind of equation, so it's containing two parts: the filtering parameters part and excitation part, and it is estimated based on minimizing the prediction error. So now we are ready with the input linguistic feature and output acoustic feature. The next step is we are trying to find some model to generate to do this conversion. So one of the famous model is the HMM model. In HMM model, each phoneme is modeled with HMM model from the what we have obtained the linguistic feature and to the output acoustic feature. Actually, for the phonemes, for each phonemes, clustering tree is conducted to cluster the context feature, because as we imagine that for each phoneme, the context information will be quite variated. So we need to summarize what information is related to what acoustic feature. So here, clustering tree is trying to cluster those linguistic context information that is common in the output acoustic features. That means some of the linguistic environment can be modeled together for the output speech. And this is actually one kind of technique to let us avoid such a case that when the linguistic context information is not covered in the recorded corpus. Right. So here the decision tree is trying to ask the question that is the right phoneme voiced, or is the current phoneme the R, and then in each node it is divided into two parts. That means the linguistic feature space is divided into two parts, right, at each node. And then until the leaf, the Gaussian mixture model is used to model the acoustic distribution based on the input linguistic features to model the output acoustic features. So we can imagine that if we have the linguistic vector, now we will try to search which leaf node is related to this linguistic feature. and then we use that GMM distribution related to this linguistic feature to generate the acoustic feature, right? Okay, so decision tree is good because it divide and conquer the linguistic feature space into several parts and then do the model. But the limitation is because of this division, so the feature is divided into several isolated parts. So we will adjust this. We will talk about this later. So here we just know that the limitation is data fragmentation. Okay, so here we talk about the HMM based model for doing the linguistic to acoustic mapping. Now we talk about the deep learning revolution. We see how deep learning changed this kind of modeling. As we know, deep learning thanks to the big data and big resource, because today we have crowdsourcing to provide huge amount of data, human knowledge data, and machines, cloud computing for us to do big computation, and also tools, open resourcing tools for us to do the deep learning algorithms like this. So this is deep learning, so I think I don't need to talk very much of deep learning today, but we are still very impressed that some kind of models that use hundreds of layers that can achieve the state-of-the-art performance in image, some task of image classification like this. So now we look at what is, since 2006, deep learning is introduced to speech area, first in the speech recognition, and then we will talk more of how deep learning is introduced to text to TTS area. Now the first part that is changed is the G2P part, that is how we predict the pronunciation. So remember, previously we talked about text normalization, PostTaking, word segmenting, those many part of techniques just for the goals to obtain the pronunciation. Now we can do it in such a compact model, just in one model. The input is the characters. And this model is actually based on the popular bird architecture. So this is just give you a sense that now we don't need to do so many subtasks. We just use one model. But we just want to use model. You just use one model, but the performance is better. Though we know that later we will talk, we lose some insight into the model. But at this moment, we say the performance is good and the model is simple. And the second part is the linguistic to acoustic mapping, right? So previously we used HMM in this part. Now we use DNN. And there are several pioneer works that is introducing DNN into this part. Like CHK, actually our group. I advertise our work here. So we try to use DBN to represent the joint distribution of the linguistic or acoustic feature as P x given y. And here is the state level modeling. State level means the HMM state. That is just HMM state. And also the work from Google used DNN to mapping this conditional distribution from linguistic to acoustic. And also USTC and Microsoft modeling, trying to replace, trying to use the decision tree, replace the decision tree with such kind of deviant. Oh, sorry. So use the deviant to replace the GMN distribution in the conventional way. So here's the IPMG DNGP. So it's just use the last hidden layers as the output as the input of the GPU process. We just want to show here that we use the DNN to replace some part of the conventional method. Why do we use this method to replace these parts? Here is so, and also because as we know that DNN has a limitation that it only focus on fixed time span. That, as we mentioned, that is only at the state level. So now we we may think that because the longer distance context should be useful for the mapping, so LSTM is used, and this is also a familiar problem and task. And what's interesting is actually we also would like to model the relation in the output acoustic, not only at the input linguistic. So as we see here, this is the structure that is with iron, and then in this structure the connection is built from the previous output to the next output. What does it mean? It means that we hope the prediction at this point will consider the output at this point. So that means when we are modeling YT, we also have the information from Y less than T. So let's summarize the advantage of deep learning. So as we say, decision tree segment the training data into isolated part, but deep learning can model this linguistic feature as a whole. So here, for example, when we add a node, it's actually separate the linguistic feature space into two parts, but these two parts will still considered in the consequential layers. And the second advantage is previously we used the GMM model that is with diagnostic covariance matrix. That actually we assume that different output is independent, but the modeling of different output steps should be desirable. So here deep learning provide the flexibility of modeling such kind of relations. So we can see the equation become more and more complex, but actually more and more powerful because it considers more and more information. And the other advantage is it deep learning implicitly mimic the layered structure, layered production process of human. Right. So now we finished the part of statistic parametric speech synthesis, consists of HMM and DNN. Now we will talk about the recent improvement based on such kind of method. Since 2016, lots of new models are proposed, and actually we can summarize these many models in one mechanism, that is attention mechanism. And we will now show why we use attention to improve the previous models. So what's the problem in the previous model? The problem is in previous model we are optimized using two separated stage. Because as we know, the input linguistic feature that is like the syllable sequence. And the output acoustic feature, that let's say if we use the capsule frames. These two sequences not the same length. It's not of the same length. So we first need to align these two sequences, and then we do the frame level mapping. So it's like this. We first align the input and output, and then we do the frame level mapping. And as we know, these two parts in previous model, we use a duration model to predict what's the duration for this unit. What's the duration for this unit? And then based on this duration, we upsample the input linguistic feature into the output acoustic feature. And then we do the mapping, the acoustic model. So as we know, there is some problem here because the alignment, we rely on alignment label to do the duration model chaining and also do the acoustic model chaining. But this label may contain human error or labeling error. So this is not necessarily the optimal. So it is desirable to use a model that can search for the optimal duration for each phoneme by itself, so that no annotated duration is needed. So the attention mechanism can play such a role that bring the alignment model and the acoustic model together like this. So, for example, if we have such an input linguistic sequence, then we predict the attention of how much attention should be paid to each step of this linguistic sequence. That means when I'm predicting this acoustic step, I will ask the model how many attention should be paid to the first note, to the second note, and the third note. And then this, based on this attention, we combine the input linguistic feature into hidden representation. That is called a context hidden representation. And then based on this hidden representation, we predict the acoustic model. But we should know that this whole process is in one model, so it can be optimized by itself. That means this attention, attention is searched by the model by itself. So next step, how much attention, and then generate output. So this part, the backbone of this model is the attention. So I may not have time to talk very much about attention, but it's actually trying to find, like in this equation, we can find trying to project the input features into the space, into a hidden space, and also project the output acoustic feature into a hidden space. These two hidden spaces is the same hidden space. And then in this hidden space, the two projected vectors can be compared, whether they are highly correlated. If they're correlated, then the attention should be higher. This is intuitive explanation. So, but the naive, the vanilla attention mechanism is not enough, because in speech, in our area, we know that the generation of speech is actually a monotonic process. It's easy to understand, right? So it's desirable to integrate such kind of monotonic mechanism into the attention process. So here, researchers propose the location sensitive. That means when you predict the attention, it should concern which part it is at which part of the speech. So it's probably in the middle part of the speech. The model probably is not desirable to focus on the very beginning part or the very end part. So now we finish the attention part, and then recently people move further to the step that we don't need to rely on the parametric representation. Very careful decide parametric representation. We can directly model the waveform directly. So here the output is different. Now we are modeling the waveform points, the signal points. And this impressed work is proposed by Google, the WaveNet. I believe lots of you heard about this. So the WaveNet originally is proposed to doing the job still in the two-step stage, the two-step architecture. That means the WaveNet model still needs the duration information and the linguistic features. But let's first look at how WaveNet is working. So at every step, when we have the prediction of the previous step, it is used for the second step, for the second step, and then based on the previous output, it try to output the next step. And these are all operated at the waveform level. But later, WaveNet is used as the vocoder, called neural vocoder. That means here the linguistic feature is changed to some kind of acoustic feature. But this is the story later. Okay, so originally we have such kind of long pipeline text-to-speech. Later we gradually combining several sub modules of this pipeline, and then we combine the linguistic to state cluster and state cluster to acoustic. We combine the acoustic smoothing. We combine the this is WaveNet. We combine even the vocoder, and we do the sequence to sequence mapping from the phoning, or even from the character to the output speech. Here, chart to wave is misleading, but this is the original net in the paper. But it's actually still predict the acoustic feature and then use a neural vocoder to output the speech. And here, different voice by Baidu, and voice loop, and the tachotron. And tachotron is one of the famous model that now lots of the research is based on. So let's listen to the how is it like.
The quick brownie fox jumps over the lazy dog.
So this is the tachotron output. So here we finished the previous part from the statistic parametric synthesis to how it is changed by attention-based model, how it is changed by WaveNet that you then drop the vocoder. So how is the future of text-to-speech? Now text-to-speech is already state-of-the-art system, already can generate close to human quality of speech. What's the future? So maybe more research effort will be devoted to expressive speech. That means we would like to generate the speech that is more animated, that is fit for different application scenario. The expressive styles, including like different intonation or different emotions, and the basic structure is like this. So based on the input text and input style specification, we use the expressive text-to-speech model to generate the output speech. But the challenge is how to specify the style. Take the emotion as example, as we all know that emotion is quite subjective, both in the generation and the perception. So how to provide the data for the model to learn is a challenge. So like we have two ways to approach to do this. The first is rely on artificial notation, like we can use the for emotion big six, happy, sad, angry. But these are discrete labels that cannot express those kind of complex information. Like if I am both happy and both angry, then this emotion cannot be correctly specified. Also, try to address this problem. Some research also use dimensional values, like I try to specify how is the arousal value, the dominance value, such kind of value, trying to use such kind of continuous space to specify the emotion. Also, this kind of space is when we use this space to annotate data, and the data is actually quite ambiguous and unreliable. And also some research try to derive automatic annotations from data. Like we use, like here, some research use the clustering method to cluster the corpus into several clusters, and then these clusters is used as the annotation. But the limitation is the clustering and the text-to-speech model is separated. It's separated chaining. So it's desirable to combine these two together, and also to use unambiguous method to specify those styles. Don't like specify the emotion. So how is it? How can we do it? So like now, normal method is trying to use exemplar to describe the style. So it's like this. If you want to synthesize some kind of emotion, you don't need to tell me what's the emotion name or what's the dimensional values. You just provide me a speech that you think is conveying the desired speech, the desired style or emotion that you want. And then I will synthesize a speech that is similar to this emotion or this style. So some works trying to learn the style representation from such kind of exemplary speech that you provide, and then based on this representation to generate the output speech. So here we will introduce one of the work among the three pioneer work in this direction. That is also our work. Let's look back at the natural text-to-speech, that is like the Stefan Tekochon. Then the input is the linguistic feature and the output is the acoustic feature. And when we train the model, if we doesn't provide the style information, then the output speech is actually averaged. But we would like to provide a model what's the distribution of the variation from the neutral or average speech to the target emotion. It's like, what's the difference between the neutral emotion and the target emotion? So, like, we can use the output difference, like here we term it as the residue error. And use this residue error, we encode the error into hidden embedding, and then based on this hidden embedding, the output speech, the output target style speech is generated, and this output style speech is expected to be similar to this exemplary speech that is provided. So here is the detail of the error encoder. The idea is trying to model the temporal information of the residual error. So we here use recurrent network, and so the advantage of such kind of structure is now the style inference and the style synthesis is combined together. We are still talking about combining two sub-modules into one model. And so this one model can be jointly optimized. And then we can also leverage some already trained average model for generating the residual error, and this model can also be used for rapid adaptation, because you only need to provide one exemplary utterance, then the model can be adapted to the target emotion. So here is some of the results that so this column is the target utterances that is used as the example, and the fourth column is expected to have the similar style as the as specified by the input example. So let's try.
Oh, Juliet, my Juliet.
Here is the baseline techotron.
A few hours later, the readings have taken place.
Here is the let's look at another output.
Soon will sound asleep. A few hours later, the readings have taken place.
Yeah, so we can compare.
A few hours later, new readings have taken place.
The volume is limited.
A few hours later, the readings have taken place.
So you can see that these two sentences already, although they have the same content, text content, but they have different style that is similar to the previous specifying example. So here we also find some interesting phenomenon that the embedding can use to control the intonational prosody. Like here we show that we use different embedding, then we can generate different pitch counters at different level. Here we draw the conclusion. So as we saw that the big data and big resource has boosted the research very much, and it also structured the research in these years. And we also see that when we're compressing the submodels into one compact model and optimize it together, we can achieve great success. And we believe, because we already see that increasing data hub has changed the research very much, and in the future it will also deeply affect the future. But the question is end-to-end the future of text-to-speech? It's a yes and no question. So obviously, the yes, we can have better performance by the joint optimization, but this also means we need to provide much more data, and also the model is lack of controllability and interpretability. But we are still very we think the future of text-to-speech is quite bright, because in speech there are many informations in speech we would like to model, we would like to generate, like different meaning, different intent, emotion, speaker ID, and even the education or the cognitive levels of the speaker. So hope there are much more impressed work in the future that we can study. Thank you.